Alright, so today I'm going to be explaining another important article with the title The Power of Recursion in Graph Neural Networks for Counting Substructures. This paper in 2023 from MIT. So to achieve a graph representation, most graph neural networks follow two steps. First, each graph is decomposed into a number of subgraphs, which we call the recursion steps, and then the collection of subgraphs is encoded by several iterative pooling steps. Why recently proposed higher order networks show a remarkable increase in the expressive power through a single recursion and larger neighborhoods followed by iterative pooling. The power of deeper recursion in GNNs without any iterative pooling is still not fully understood. To make it concrete, we consider pure recursion-based GNN, which we call recursive neighborhood pooling GNN. The expressive power of it and its computational cost quantifies the power of pure recursion for a graph representation network. And we quantify the power by means of counting substructures, which is one main limitation of the main message passing graph neural networks, and show how it can exploit the sparsity of the underlying graph to achieve low-cost, powerful representations. So we aggregate the messages and then we update it. But message passing neural network cannot count substructure with 3 nodes or more. Since the two graphs on the left result in the same node representation as the graph on the right. So we have, as I said, we have aggregation. So once it is aggregated, then we can update using this combined function. And then we have local relational pooling. That the strategy of recursive pooling has previously been used for counting in local relational pooling. And it relies on an isomorphic encoding of subgraphs, which is expensive. The relational pooling it require order of k factorial time for a subgraph of size k. Other high-order GNNs would be expensive too, as high orders are needed for complete isomorphism power. The idea of having one recursion and then using a base network is also mentioned in this article, where the authors consider message passing neural network as base networks and show how the model can distinguish most regular graphs. A major difference to our RMP is that our recursion uses subgraphs of varying sizes and structures. Many of them, much smaller, adapted to the graph structure and a specific counting task. Thus, the recursion pooling operation not only improves the expressive power, but can also make it more adapted. So the recursive neighborhood pooling operation takes a graph with node features and a sequence of neighborhood radii for different recursion steps and returns a set of node encodings. So for any V, for any vertex, like this one, for any vertex, the method first constructs V's neighborhood by adding an additional node features. by marking node labels with structural information in this step, we bypass the reconstruction conjecture. Next, we aggregate over subgraph representations. In the base case of tau is equal to 1, we simply aggregate over the input features. If tau is greater than 1, we recursively represent neighborhoods of nodes in G. To compute representation of node, this is done by forming the message H hat. So for aggregation, we can use the injective multiset function form that is in this paper, in this article in 2019. The final readout aggregates over the final node representations of the entire graph. Figure 2 illustrates with recursion parameters. So while message passing neural networks also encode a representation of a local neighborhood, the recursive representation differ as they take into account intersections of neighborhoods. As a result, they retain more structural information and are more expressive. So first, we are given a graph and the recursion parameters, also node features. Then if tau is equal to 1, then this is just a simple representation, which, as you see, is just using multi-layer perceptrons. But else, if it is tau is not 1, then we go through this, and we have the node attributes. We sample our graph is now G of a neighborhood of R1 of V, node V. So we get the neighborhood, and this is how we recursively do the neighborhood pooling. So now we can count the substructures. Let G and H be arbitrarily potentially attributed simple graphs, where V is set of nodes. Also for any S, let G denote the subgraph of G induced by S. The induced subgraph count function is defined as this. So this is the, for example, number of subgraphs of G isomorphic to H. There are two other important definitions before we carry on. So let H be a simple connected graph. Define the covering distance of V from S to be the maximum. So very natural distance. D is the shortest path distance in H. And then let H be a simple connected graph. A permutation of vertices is called vertex covering sequence if and only if there exists a sequence R, which is called a covering sequence. If you draw it, you will notice how important it is. But they just use this to prove some theorems, and they do test on Erdős Reni. Erdős is a great mathematician. If you want to read graph theory, you will probably see the random graphs and what he has done. And that's it.